Hello. So in this presentation, I would like to talk about three main things. So the first of which is, what is the gas and particle composition of the atmosphere? What are the 5 layers of the atmosphere? And how is energy transferred around in the atmosphere? And there's your essential questions. So by the time I'm done with this discussion, you should be able to answer these 3 questions. And so I'm going to challenge you to write down these 3 questions in your notes and make sure that by the time this is done, you can answer these 3 questions. Your vocabulary for this section is here. You should be able to define these words. You'll notice that these first 5 words are the layers of the atmosphere. The atmospheric layers are here. And then the 3 ways that you can transmit energy are listed right below those. You should be able to define those words, understand where they are found, and how they can be described or defined. And I'm going to move a little bit quick. I want to make sure that I am going to have enough time to cover all these topics. And adjust that. Okay. Hopefully I remember to cut that out. Okay, so the first thing is atmospheric composition. So air in the atmosphere is a combination of all the gases, such as nitrogen, oxygen, other particles such as dust and things like that, water droplets, ice crystals. Different things may or may not be in the atmosphere depending on the time of year and the situation. See if we can adjust this. There we go. So atmospheric composition. So there's permanent atmospheric gases. You can see this little pie chart here. In this pie chart, we see that 78% of the atmosphere is nitrogen, 21% is oxygen, and then you have less than 1% of argon, and then these other ones are in very trace amounts. Notice that water vapor is variable. Water vapor can vary between 0 and 4% of the atmospheric content being water vapor. And that's also going to be a function of temperature as well and other factors. Notice carbon dioxide is a very small amount, and that's also variable. And I gave the example in my class that, if we're all in the classroom and the air isn't cycling, we could start building up carbon dioxide in the classroom, and this number can climb. So during the past 150 years, the concentration of atmospheric carbon dioxide has increased due primarily to the burning of fossil fuels. And this may potentially be problematic. And you may have heard some conversations about people talking about climbing carbon dioxide. The reason this is the reason people get so excited about this is we know that Venus has experienced what we call a runaway greenhouse effect, where there's so much carbon dioxide that the carbon dioxide is intercepting the infrared radiation that's being emitted by the planet. And so that energy cannot escape. And since it cannot escape, it continues climbing, millennia after millennia. It's over time, we're now up to over 700 degrees temperature around the day or night. And so basically on Venus, it's very, very hot. It's impossible for life to exist on Venus as we know it. And if Earth was to have a similar runaway greenhouse effect, that would be very, very bad. Life would not exist on Earth. And so people get a little excited when the carbon dioxide levels start climbing because they don't want us to turn into another Venus. All right. In this particular slide, we're noticing that this is talking about ozone and oxygen, and how if you combine an oxygen molecule with an additional oxygen atom, you get this triplet of oxygen atoms that we call ozone. Molecules of ozone are formed by the addition of oxygen to oxygen molecules. It's a little bit more complex than that, but we're just going to pretend like it's that simple. Typically, radiation from the sun is actually going to cause a cleavage effect to one of these, and it's going to cause a very reactive superoxide atom to react with oxygen, forming ozone, but it's basically what they're saying. So in the atmosphere, ozone is going to help UV rays from reaching the Earth's surface. And so as you can see in this slide right here, the ozone layer is going to intercept a massive majority of the UV rays that are trying to hit Earth. So this is filtering us. This is almost like sunglasses. And the analogy that I gave in class was I wanted the students to imagine that the walls are opaque to some frequencies of radiation. So for example, Visible light, we can't see through the walls, but the visible light comes clean through the windows, no problem. However, there are some frequencies that do pass through the walls, like radio waves. Your cell phone can easily connect to the cell phone tower right through the wall, no problem. Just like the walls block visible light, I explained that this ozone that's in the atmosphere is going to absorb some portion of the UV ray. It doesn't block all of it, so it's not like an opaque wall. It's more like sunglasses. Like like if your eyes could see in UV, the ozone layer would block a large portion of that, and the sky would look dark to your vision if your vision was specifically only seeing the UV. It would at least look darker than it would if you were able to see through the atmosphere without the ozone layer.
Please pardon the interruption.
All right, sorry about the announcement beep. So there's a lot of things in the atmosphere. Like I was saying, the first layer of the atmosphere is called the troposphere. This is the lowest layer. This is the closest layer to Earth's surface, and the troposphere contains most of the mass of the atmosphere, and this is due to gravity. Weather is also mainly occurring here, so most of the air molecules that exist are in this layer. And as you increase in elevation in the troposphere, your temperature is going to decrease as your altitude increases. In other words, it's going to get colder and colder as you get further and further away from the ground. All right, and you're going to continue to be in what we call the troposphere until there's a reverse in this, where the temperature starts going the other direction. In other words, it's going to start getting warmer and warmer. And until that happens, you're still in the troposphere. And so like I introduced the stratosphere, So in the stratosphere, just above the troposphere is the stratosphere. And we actually call the tropopause the layer between the troposphere and the stratosphere. So once you're in the stratosphere, this is where the air temperature is going to increase with altitude. So it's going to get warmer and warmer. So the stratosphere contains the ozone layer, this layer that I said is going to intercept the majority of those UV photons, those UV rays, that UV light that is very damaging to both humans and plants and things like that. Okay, next we have the mesosphere. Above the stratopause, so there's a stratopause separating the stratosphere from the mesosphere. And above the stratopause, above the stratosphere, is the mesosphere. And in the mesosphere, you're going to have this trend where air temperature is going to decrease with altitude, just like with the troposphere. So the troposphere, like the mesosphere, is going to have temperature decreasing as you get higher in elevation, or the further you go away from Earth, it's going to get colder and colder again. And the temperatures will stop doing this with altitude at the mesopause. And that's when we transition into the thermosphere. So the thermosphere is the layer above the mesopause and contains the ionosphere. And as you can see in this picture, the ionosphere is where you're going to have these magnetic field lines that are going to concentrate solar winds and create this amazing effect that we call the northern and southern lights, or the aurora borealis or aurora australis. Okay, next we have the exosphere. The exosphere is the outermost layer in Earth's atmosphere and can be thought of as the transitional region between Earth's atmosphere and outer space. So as we said, 5 layers. You can kind of think of this like cake with multiple layers. The layer closest to the ground is going to be the troposphere, then the stratosphere, then the mesosphere, then the thermosphere, and then the exosphere. Energy is transferred in the atmosphere. So the total energy of the particles in an object due to their random motion is called thermal energy. Another example I like to use is billiard balls, like when you're playing pool and you hit the cue ball, you're delivering that cue ball with kinetic energy. And as that kinetic energy is passed from one billiard ball to the next, you can think of this as the transfer of energy. And if you think of particles like atoms or molecules with molecular kinetic energy, they can pass on that molecular kinetic energy. And this is what we call thermal energy. So radiation. Radiation is the transfer of thermal energy by electromagnetic waves. So thermal energy is transferred from sun to Earth by radiation. We can't really transfer energy in any other way from the sun. I mean, you can argue that the solar winds transport some amount of energy, but that's a little bit more complex than convection, so we're not going to go there. So the way this affects Earth is incoming solar radiation is either reflected back into space or absorbed by Earth's atmosphere at its surface. So the sun is beaming down on Earth. Solar radiation can be absorbed by Earth's surface. Solar radiation can be reflected out into space. And the amount of solar energy that's reflected out into space is a function of what we call albedo. That's the reflectiveness of the Earth. Infrared radiation can be emitted by both the atmosphere and by the surface of Earth. And the thing that traps infrared radiation is the carbon dioxide and water vapor, but we don't really talk about that. And those can cause the Earth to heat up like a greenhouse. And we call them greenhouse gases. There's other gases that do the same. And then there's some reflection. You can kind of just go through this little picture here. I'm going to try to go quickly through this so I don't run out of time. I'm trying to keep this under 15 minutes. Once again, radiation. So conduction. Conduction is the transfer of thermal energy between objects when their atoms or molecules collide. Kind of like I talked about billiard balls, right? By touch, you can transfer heat. For example, in class I showed with a thermal scan. I have a thermal scanner, and I scan the desk showing the temperature of the desk, but as I rest my hand on the desk for only a few seconds, I can scan where my hand was just at, and I can detect a measurable temperature difference. The temperature jumped by like 10 degrees just having my hand resting on the desk for just a few seconds. And this is called conduction. This is where we're transferring thermal energy between objects when their atoms or molecules collide or come into contact with each other. Then we have convection. Convection is the transfer of thermal energy by the movement of heated material from one place to another. So if we think of gases or liquids, those are both fluids, and fluids can flow or they can move. And typically what they do is, when you have a fluid, if you heat up part of that fluid, the part that you heated up will rise up above parts of the fluid that are not as heated up. So when I say heated up, I mean that they're just some amount warmer than the surrounding fluid. And when that happens, they'll rise up and float on top of the colder fluid. And this movement of masses of fluids is called convection. And that's this transfer by movement of atoms or collections of atoms. Okay, so that pretty much wraps up this section. Those are your essential questions. I hope you can now answer those questions based on that. If you can't, I highly recommend you go back and watch the PowerPoint again to make sure you understand it. Those are your vocab words. Make sure you understand which layers correspond to which position. Troposphere closest to the Earth, and then exosphere furthest away, and then the other ones in between in that respective order. We talked about radiation, we talked about conduction, and we talked about convection. And so make sure you understand those different types of heat transfer. And I hope this helps. Thanks for watching. Don't forget to subscribe.